I want to spend a little bit of time here talking about the area problem, even though we're not going to get into the details of it and study it in depth until later in the year. Um, we are going to start the year with a unit on limits, and we're going to use those limits to help us solve the tangent line problem. If you remember talking about Jordan Hicks and throwing a fastball and figuring out how fast that fastball was going, we're going to use limits to actually solve that problem. And ultimately, we're going to use limits to solve the area problem also. So I want to talk about how we're going to approach the area problem, and then that'll kind of lead into why we need limits to help us with that. So in this particular problem, we have a car that's accelerating. It's going from 0 to 60 miles per hour in 2.3 seconds. That is pretty fast. Making some assumptions, which aren't very good assumptions, and we'll talk about that in a little bit. But making some assumptions, we can model the velocity with this function right here. So that's going to give us the velocity in feet per second at any given time after the car starts accelerating. And the question then is, how far does the car go during the 2.3 seconds that it is accelerating? So I want to start here by looking at a table of values. And this table I created by just plugging in different t values and figuring out what the velocity is at any given time. So for example, I'm going to just pick one of these here. After a second of acceleration, the car is going to be going 38.261 feet per second. So that's not that useful to us because it's not traveling that speed over the course of a second. If it did travel that speed for a full second, then we can say it went about 38 feet. However, it's accelerating. It's going faster and faster and faster. So what I'm going to do is I'm going to make the assumption that it's going that speed, but for a short period of time. And since I broke this table up into tenths of a second, I'll use that. So you may remember from physics, there's a formula that says rate times time equals distance. So we can figure out how far something goes if we take its speed times the time that it travels that. So in this particular example, we'll say that it's going 38.261 feet per second for a tenth of a second. Okay, not for a full second. And that's going to give us 3.8261 feet. Okay, now that's an approximation. It's not actually going this speed for that full tenth of a second. I know a tenth of a second is a pretty short time period, but it is going faster at the end of that tenth of a second than at the beginning. But it's going to be pretty close. And then we could do that for each of these intervals. So if we do that, we can add up all of those distances that we get that are approximating how far it goes each tenth of a second and get a distance. I want to look at a graph here, and on that graph, what we just did is the same thing as saying at this 1 second mark, we'll just assume that the velocity is straight here. That's not very straight. We'll assume that the velocity is straight here for that full tenth of a second. And essentially what we did is we found the area of this rectangle because the width of the rectangle is a tenth of a second, and the height of the rectangle is the value of the velocity function at this time, which is that 38.261. And if we find the area of that rectangle, we multiply height times width, and we do the exact same calculation that we just did here. So this is the height of the rectangle, this is the width of the rectangle. So by adding all of these up, then what we're doing is we are taking a bunch of these rectangles and adding up all of those areas. And pardon the sloppiness here, but hopefully you get the idea. Now, I think that by looking at this picture here, you're going to see a little bit of a problem, and I already addressed that problem. I mentioned that what we're finding here is just an approximation, so that 3.8 feet that it traveled during the time interval from 1 to 1.1 seconds, and then it's going to be about 4.2 feet that we're approximating here, and about 4.6 feet here. Each of those is an approximation that is traveling over that interval. Well, if this is represented by an area, then what we really want to be more accurate is we want to know what's the area of this region here. So thinking back to your geometry, this is actually a fairly easy problem to do. What we can do here is we can find the area of a trapezoid because these two sides are parallel, average the two bases, and multiply by the width. So essentially, what we're doing is we're taking those two, we're going to average them and multiply it by a tenth of a second. That's going to give us an exact area. So, what we can actually do with this problem is we can just find the area of the whole thing all at once. I didn't actually need to break it up into tenths of a second. So if we look at this shape here, solving the area problem, which is going to tell us how fast our Tesla, sorry, not how fast, how far our Tesla travels, is the same thing as finding the area of this triangle. So that area is going to be 2.3, and I'm going to include units here just for fun, 2.3 seconds times, at the end it's going 88 feet per second, and then divided by 2. So area of a triangle, base times height divided by 2. I don't even know what that answer is. It doesn't matter here. I do want to point out, though, that our units are going to end up being feet, and that's going to give us the distance that the car traveled over this 2.3 second interval. And it's actually exact. Now, the problem is this isn't what the acceleration is going to look like, or I should say the velocity. The velocity is not going to be a straight line function. It's going to look more like this. So this is an electric motor. Combustion engines look a little bit different, but it's going to accelerate faster at first, and then it's going to kind of taper off. So in this case, if we model this, and this is a model here, we get a function that is a little bit messier, quite a bit messier actually, and we can look at a table of values just like we did before. And the problem now is we can't find this area using geometry. So the answer to the problem that we're looking for is going to be that area, but geometry is not helping us. So this is where what I did earlier by looking at one interval and finding an area associated with just that interval is going to give us a better approximation, or really the only answer that we could get. Now, you might be able to guess this, all of these areas added together, that's going to be an approximation. You can see it's not going to be accurate. In fact, we can say that it's going to be an under approximation because it's missing a little bit of area up there at the top. But we can make this more accurate by doing a couple of different things. Maybe over this interval from 1 second to 1.1 second, we do a trapezoid. So it looks like a trapezoid is going to be a pretty good fit for the picture. And it is a pretty good fit. It's going to be a little bit off. If we were to zoom in on this region here, we'd have something that kind of looks like this. So we would have a little bit of a gap there, but it's going to be a lot closer than using a rectangle. So we could find the area of that trapezoid and find the area of all 23 of these trapezoids and add them all together. That would give us an approximation, but no matter what we do here with our geometric shapes that we're familiar with, we're just going to get an approximation. So we can make it more accurate. We made the rectangle more accurate by using a trapezoid. We could also make it more accurate by using more intervals. So instead of 23, use twice as many, say 46. So instead of every tenth of a second, we use every 500ths of a second. If we do that, we get a lot more detail, but also a lot more work. This is, in fact, so small, it's kind of hard to read because we got so much here. But I just kind of want to talk about the idea here. So instead of going from 1 second to 1.1 seconds, we can go from 1 second to 1.05. And when we do that, we're going to get something that's a little bit more accurate. I talked about the same idea with our fastball. So we look at snapshots of the ball at two different time periods, over a time period that's getting smaller and smaller and smaller, and we can make it more and more accurate by picking a smaller and smaller interval. Same thing is true here. We pick smaller and smaller intervals, and we add up more and more and more shapes, but we're getting a more accurate area answer. In this case, the more rectangles or trapezoids or whatever shape we're using, the more of them we use, the more accurate our answer is going to be. So this idea here is we can make the answer more accurate, even if we have a pretty accurate answer, just by using more, by choosing a different number of rectangles. And that idea is kind of the same idea as what we had going on with the fastball and the tangent line problem.